Welcome, everyone. You've done the really hard work, right? The late nights, the patient recruitment, collecting all that data. But that final step, turning all that hard work into a credible publication, well, that all comes down to how you report your statistics. And this isn't just about getting the numbers right. It's about telling the true story of your research. So in this session, we're going to go way beyond the basics. We're going to give you, as physician researchers, the advanced framework you really need to master this. So let's start with the hard truth, the reason we're all here. The entire biomedical field is dealing with a major reproducibility crisis. And as Dexter and Schaefer put it so perfectly, one of the main culprits is exactly what we're talking about today, how we report and how journals review our stats. Now, this isn't some small clerical issue. No way. It's a fundamental threat to the trust people have in our work. When reporting is sloppy or vague, it makes it impossible for others to replicate your findings, and that calls everything into question. So, here's our game plan. First, we'll look at why so many past attempts to fix this problem have, well, failed. Then, we're going to get practical and dissect a real-world blueprint from a top journal. From there, we'll boil it all down to some core principles. And I'll give you a field guide to the most common errors so you can spot them and avoid them. And, critically, we're going to spend a good chunk of time on what I think is the most important shift in modern research, moving beyond just the p-value to what really matters, clinical relevance. And don't worry, we'll wrap up with real, actionable solutions for both the system and for each of us.
Okay, let's dive right in. It seems pretty logical, right? If you just give authors better instructions, or maybe a checklist, the problem should just fix itself. But the real story is a lot more complicated, and frankly, a lot more interesting. So why have these common sense fixes fallen so short?
This timeline tells a really fascinating story, often called the Loftus effect. Back in the mid-90s, an editor named Jeffrey Loftus decided to mandate error bars in his journal. He hoped it would get people to think beyond just p-values. And on the surface, it worked. Usage shot up from 10% to around 40%. But, and this is the key part, look what happened the second he left. The numbers immediately started to drop. A deeper dive showed what was really going on. Researchers were following the letter of the law, but not the spirit. They added the error bars, sure, but their thinking, their interpretation, it was all still stuck on null hypothesis testing. They just tick a box. And that's a huge lesson for us. Simple instructions without a real change in how we think and practice just don't create lasting change.
So what's the next logical solution? Checklists, right? Well, this slide is pretty damning. We have these famous, well-designed checklists like SQUIRE and STROBE. But look at the data. SQUIRE? Basically no change in reporting quality. STROBE? Well, reporting did get better, but it was already trending up anyway. The checklist itself had no real impact. But here's the kicker. The BMJ, one of the top journals in the world, mandated the STROBE checklist. They made it a requirement. And the result? Their reporting was no better than journals that just suggested using it. The takeaway here is pretty clear. Checklists can just become another administrative hurdle, giving us this false sense of security without any real substance.
Okay, so if simple instructions and checklists don't work, what does? Well, to figure that out, let's stop talking theory and get practical. We're going to take a close look at the incredibly detailed section-by-section checklist used by the journal Anesthesia and Analgesia. This is a fantastic model for the kind of detail and clarity we should all be aiming for. You can see the rigor starts right at the top. The abstract has to be a perfect little miniature of your entire paper. The intro isn't just fluffy background, it's where you have to explicitly state your primary and secondary hypotheses. In the methods, everything has to be crystal clear. Who did you study? What exactly did you do to them? What were you measuring? And pay really close attention to this last one, because this is a total game changer. For intervention studies, you have to state before you even run the numbers what you as a clinician consider a meaningful difference. This isn't a statistician's number, this is your clinical judgment, and it becomes the measuring stick for your entire study. The big theme here is logical integrity. Your results section should be totally predictable based on your methods. No surprises. Your tables and figures, they have to make sense on their own, and consistency is non-negotiable. Then in the discussion, you can't make these huge leaps in your conclusions that your data don't support. And finally, integrity. You have to be upfront about your study's limitations. And, most importantly, you have to resist that temptation to p-hack, where you torture the data until it finally confesses to something significant. You've got to be honest about which analyses you planned from the start and which ones were just exploratory. Okay, that journal checklist gives us a great structure, but now let's zoom out a bit. Let's distill all those specific rules into some core guiding principles that you can apply to any paper you write, no matter what journal it's for.
These come from established guidelines like Sample and the Canadian Journal of Anaesthesia.
The number one principle is radical transparency. The goal is simple. Could another researcher, with your data, reproduce your analysis exactly? That means you have to report everything. Did you transform a variable? Did you group ages into categories? You have to say so. And for your main analyses, it is not enough to just say, we ran a t-test. You have to explain why a t-test was the right tool for the job, and confirm you checked its assumptions. If you ran a bunch of tests, you have to explain how you controlled for the fact that you were more likely to get a false positive. And hey, a simple one that gets forgotten all the time, just name the software you used.
Now let's get into the nitty-gritty of the numbers themselves, which this slide lays out perfectly. You have to use common sense with your precision. Reporting 4.3 patients is just silly. Always use the mean SD format because plus or minus can be ambiguous. If your data is skewed, the median is your friend. It tells a much truer story than the mean. And this is a huge one. Report your exact p-values. A p-value of 0.049 and 0.0001 both count as less than 0.05, but they tell completely different stories about the strength of your evidence. Just writing NS for not significant is just not good enough anymore.
Regression. It's powerful, but man, it is filled with traps. You have to be totally transparent about how you chose the variables that ended up in your model. You also need to check for collinearity. That's just a fancy way of saying your predictor variables are so tangled up with each other that your model can't figure out which one is doing the work. And here's one of the biggest mistakes I see: cutting up a continuous variable like age into old and young. When you do that, you are literally throwing valuable information in the trash. And a great pro tip: rescale your predictors. An odds ratio for every 10 years of age is just so much easier to understand than for every single year.
Okay, we've laid out the gold standard. Now it's time to put on our detective hats. To get good at avoiding errors, you first have to get good at spotting them. So let's open up the case files and look at a catalog of the most common statistical mistakes that show up again and again in medical journals. Let's start with a number that is, well, it's pretty shocking. A review of some major dermatology journals found that only 7% of papers even bother to justify their sample size. A sample size calculation basically answers the question, how many patients do I need to have a fair shot at finding a real effect? The fact that this is missing in 93% of papers is just, it's a massive red flag.
And if you thought that was bad, hold on. In that same review, only 6% explained what they did with missing data. Look, in the real world of clinical research, you always have missing data. It's a given. How you handle it can totally change your results. So if you don't report what you did, your reader has no way to judge a huge potential source of bias. This chart just hammers the point home. These aren't just one-off findings. One study found that 0%, not a single paper, included a power analysis. We see that 7% number again for sample size. Only 14% even properly described their methods. We're not talking about fancy, complicated stats here. This is Stats 101. The data is screaming that we have a widespread failure to report the most basic, foundational parts of a study. So why is that missing power analysis such a big deal? Well, we have to understand the two ways we can be wrong in science. The courtroom analogy is perfect. A type 1 error is a false positive, convicting an innocent person. We usually set that risk at 5%. A type 2 error is a false negative, letting a guilty person walk free. A misdiscovery. A study's power is its ability to avoid that type 2 error, to correctly find a real effect. So a study without a power analysis is basically flying blind.
Now, beyond the numbers, the words we use can lead us into traps. Here are three big ones. First, the trend fallacy. Oh, it's so tempting to see a p-value of 0.07 and call it a trend towards significance. It's meaningless. The result is not significant. End of story. Second, misinterpreting a non-significant result. A p-value over 0.05 does not mean there is no difference. It means you failed to find evidence of a difference. As they say, absence of evidence is not evidence of absence. And finally, the big one. Correlation is not causation. In an observational study, you can only say two things are associated. Saying your drug reduced mortality is making a causal claim your study design simply can't back up. And that brings us to what might be the single most important concept in all of modern statistical reporting. For decades, the p-value was king, but we know now that a p-value alone just isn't enough. We have to move past this one number to a much richer, more meaningful understanding of what our results mean for our actual patients. So I want to ask you a question, and I want you to really think about it.
Is a statistically significant result the same thing as a clinically relevant result? Does getting that p-value under 0.05 mean we found something that actually matters? The answer, of course, is a huge no. There are two totally different questions. Statistical significance, which is what the p-value tells us, just asks how likely is this result due to random chance. That's it. Clinical relevance asks a much more important question. Is the effect I found big enough to matter in the real world? And that question is answered by the effect size, the magnitude of the finding, and its confidence interval. You could have a massive study that finds a drug lowers blood pressure by 0.1 mmHg, and it could be statistically significant, but no doctor on earth would care. That's the crucial difference. This slide is just brilliant. It lays out all 5 possible scenarios. Let's imagine we decided beforehand that a 5 mmHg drop in blood pressure is the minimum we care about. In study A, it's a home run. The result is significant, and the entire confidence interval is beyond our 5 mmHg line. It's a clinically relevant difference. In study B, it's significant, but the confidence interval crosses into that trivial zone. We know there's an effect, but we can't be sure it's big enough to matter. Now look at C. This one's fascinating. It's significant, but the entire confidence interval is in the trivial zone. This is a powerful finding. We are confident the drug has an effect, but we're also confident that effect is too small to be useful. D is your classic inconclusive, underpowered study. And E is also a useful result, not significant, and we're pretty sure there's no clinically relevant effect there either. So what's the practical takeaway? It's simple. For your main outcomes, always report the effect size and its 95% confidence interval. For something like blood pressure, report the difference in the means and the CI. For something like mortality, the absolute risk difference is incredibly intuitive. This gives your reader the whole story, your best guess of the effect, and the plausible range of truth around that guess. Okay, we've gone from the problem to the principles to the nitty-gritty. So how do we actually make this happen? The answer has to be a 2-part attack. It requires systemic changes from journals, and it requires a real personal commitment from every single one of us as researchers. The evidence is clear on what journals need to do. First, they need dedicated expert statistical reviewers on their teams. Second, they have to commit to a policy of 100% statistical review for every paper with data. The data shows that editors and scientific reviewers who are focused on the clinical story consistently miss major statistical errors. And third, journals need to understand that checklists are helpful, but they are no substitute for an actual expert review. But we can't just sit around and wait for the journals to change. The change starts with us, with our next paper. We have a 3-part responsibility. First, mathematical integrity. Get the analysis right and be so transparent that someone else could reproduce it. Second, clinical meaning. Never ever stop at the p-value. Always ask, so what? And answer that question with effect sizes and confidence intervals. And third, scientific rigor. Don't overstate your conclusions, don't confuse association with causation, and use precise language. So let's end by changing how we think about this. Good statistical reporting is not the last annoying hurdle you have to jump over to get published. It is not just another box to check. It is the absolute foundation of everything we do. It is the bedrock of credible, trustworthy, and reproducible science, and it's our professional duty to get it right.